Our century could witness the construction of cities in space. The foundational technologies for these colossal space megastructures are taking shape right now. This journey will reveal 20 specific, awe-inspiring projects that could transition from blueprints to reality within our lifetimes. You will gain a complete vision of a future where humanity becomes a true spacefaring civilization, living and working far beyond Earth. How will we power an interplanetary economy, and what might be the first permanent home for families off our planet? Which of our oldest cosmic dreams is finally within our grasp? The shift from science fiction to serious engineering began with a profound question posed in the 1960s. How would an advanced civilization power itself? Physicist Freeman Dyson suggested they might build a vast swarm of energy collectors encircling their star, a concept that captured our imagination but felt forever out of reach. For decades, such ideas remained in the realm of theoretical physics and visionary stories, grand dreams with no clear path to reality. But dreams have a way of laying the groundwork. Today, the conversation has fundamentally changed. We are no longer just asking what might be possible in a distant future. We are actively solving the practical problems that stand in the way. The true catalyst has been a convergence of breakthroughs across multiple fields. Robotics are advancing to the point where autonomous machines could assemble structures in the harsh vacuum of space. New materials like ultra-strong carbon-based composites are being developed that could withstand the stresses of orbital construction. Most critically, the economics of reaching space are being rewritten by reusable rockets, dramatically lowering the cost of transporting the first critical components. These are not speculative technologies. They are being tested and refined in laboratories and launch facilities right now. The driving forces behind this push are both pragmatic and profound. On Earth, our need for limitless, clean energy grows more urgent each year. In space, the potential for new industries, from asteroid mining to zero-gravity manufacturing, promises entirely new economic frontiers. And underpinning it all is a powerful, shared aspiration, the long-term survival and expansion of humanity beyond our single, fragile planet. We are witnessing the first tangible steps. Private companies are launching constellations of satellites by the thousands. Nations are collaborating on lunar bases, and prototypes for in-space resource utilization are being drafted. This is the essential groundwork. We are not merely planning a few outposts, we are laying the foundation for an entirely new phase of civilization, one that learns to build with the resources of our solar system. This century, therefore, is not about dreaming bigger, it is about building smarter, turning the grand architectural visions of the past into the interconnected, functioning systems of our future. The true scale of these future projects demands a clear definition. When we speak of space megastructures for this century, we are not describing the impossibly vast, star-encompassing constructs of pure science fiction. Those belong to a distant, almost mythical future. Instead, we are focusing on a new category of human achievement, one grounded in the trajectory we are already on. A 21st century space megastructure is a human-made, space-based structure of immense scale and critical function, one that is plausible with the technologies we can reasonably foresee developing in the coming decades. Think of them not as fantasies, but as the inevitable infrastructure of a species learning to live beyond its home world. Three key principles separate these plausible giants from mere dreams. First, they must serve an undeniable foundational purpose, whether that is providing permanent habitats, generating vast amounts of clean energy, or creating new transportation networks across the solar system. Second, their construction cannot rely solely on launching every single component from Earth. That would be far too costly and slow. They must leverage in situ resources, using materials harvested from the Moon, asteroids, or other celestial bodies to grow themselves. And third, each one must represent a logical, achievable next step in our expansion, a project that, once completed, would naturally enable and inspire the next leap forward. In essence, these are the bridges, the skyscrapers, and the power grids of the final frontier. They are the engineering wonders that would define our era for millennia, just as the Great Pyramids or the International Space Station define theirs. With this practical framework in mind, we can begin our journey through the blueprints for tomorrow. Our first concept is one that redefines the very idea of a space station, transforming it from a cramped outpost into a thriving, Earth-like hometown floating among the stars. The first permanent structure we are likely to see beyond Earth orbit will not be on a planet at all. It will be a bustling port of call in the emptiness between worlds, a facility known as the Lunar Gateway. This is not a simple expansion of the International Space Station. It is a fundamentally different kind of platform, built for a different era. Orbiting the Moon, the Gateway is conceived as a strategic hub, a crossroads for all our future deep space ambitions. Think of it as a combination service station, research outpost, and mission control, all floating in a special orbit that balances the gravitational pull of Earth and the Moon. Its primary purpose is pragmatic, to make everything else we want to do in deep space dramatically more efficient and achievable. The design philosophy builds on the hard-won lessons of the International Space Station, but with crucial upgrades for the harsh environment beyond Earth's protective magnetic field. Modules will be equipped with next-generation, closed-loop life support systems that recycle air and water with far greater efficiency, a necessity for missions lasting months or years where resupply from Earth is slow and costly. Advanced radiation shielding, using both materials and potentially protective water layers, will be tested here to safeguard future crews on their journey to Mars. Perhaps most importantly, the Gateway will operate in a realm of partial gravity, offering a unique laboratory to study its long-term effects on the human body, plants, and industrial processes, knowledge that is absolutely essential before we can establish permanent settlements. The station's strategic location is its greatest asset. From this orbital vantage point, a spacecraft can descend to the lunar surface with significantly less fuel than if it came directly from Earth. More critically, it can also ascend back to the Gateway with a smaller, more efficient lander, where it can refuel from depots supplied by lunar ice or from Earth. This turns the monumental challenge of a round trip to the Moon into a more manageable, modular sequence of steps, much like using a base camp on a mountain. This logistical elegance is what makes a sustained lunar presence, and the resource mining that may follow, economically viable for the first time. International collaboration is already weaving this vision into reality, with multiple space agencies contributing key modules. This shared endeavor underscores a profound shift. The Gateway is not owned by any single nation. It is the first piece of shared infrastructure for all humanity beyond our home world. As such, it represents far more than a collection of laboratories and docking ports. It is the foundational cornerstone, the first permanent address in the celestial neighborhood from which every other dream on our list will eventually be launched. Its success will prove we can live, work, and build in deep space, setting the stage for structures of even greater ambition and scale. But the Gateway is just the beginning of a much larger economic engine. Our second megastructure looks back toward Earth, aiming to solve one of our planet's most pressing challenges with a truly cosmic solution: large-scale orbital solar power satellites. Imagine for a moment a power plant of unimaginable scale, not built on any continent, but constructed in the silent expanse of space. This is the vision: vast arrays of mirrors and advanced photovoltaic panels, kilometers across, placed in a high geostationary orbit where they bask in perpetual, unfiltered sunlight. Unlike ground-based solar farms that are shackled by the cycle of day and night and the veil of clouds, these orbital platforms would generate a constant, unwavering stream of clean energy. The real magic, however, is in the delivery. This energy would be converted into a low-intensity microwave beam, a carefully calibrated stream of power directed with pinpoint accuracy at receiving stations on Earth's surface. These stations, called rectennas, would resemble vast, open field nets, designed to safely catch this beamed energy and convert it back into electricity for the global grid. The concept addresses the fundamental flaw of renewable energy on Earth, its intermittency, by moving the source to a place where the sun never sets. The engineering challenges are immense, of course, but they are being tackled incrementally. The key breakthrough that makes this megastructure plausible for our century is a shift in how we would build it. Launching thousands of heavy, delicate solar panels from Earth's gravity well is prohibitively expensive. The solution lies in using the materials we find already in space. Robotic factories on the Moon could process lunar soil into raw materials, while automated spacecraft could harvest metals from nearby asteroids. These resources would then be fed to fleets of autonomous assemblers in orbit, constructing the gigantic satellites piece by piece without a single human welder in a spacesuit. This approach transforms the economics entirely, turning space from a destination into a resource-rich construction yard. Naturally, the idea of beaming power through the atmosphere raises important questions about safety and efficiency. Research teams are already developing prototypes and running simulations to ensure the microwave beams are precisely controlled and pose no risk to aircraft, wildlife, or communities below. The intensity at the center of the receiving station would be significant, but outside its boundaries, the energy level would be no more than you might experience standing in sunlight. This isn't a weapon, it's a utility designed with multiple layers of fail-safes. Several nations and private companies now have active development programs, moving from whiteboard concepts to small-scale in-orbit demonstrations. The implications of success are profound. A single large-scale solar power satellite could provide baseload power for entire cities, offering a clean, reliable alternative to fossil fuels and ground-based nuclear plants. It could deliver energy to remote regions without the need for massive overland transmission lines. Most significantly for our broader narrative, it creates a powerful, tangible economic reason to build a space-based industrial capacity. The demand for clean power on Earth could fund the development of the very technologies, the mining robots, the orbital construction drones, and the transportation networks that will enable every other structure on this list. In this way, the solar power satellite is more than a power plant. It is the potential economic engine for humanity's entire spacefaring future, proving that the greatest gifts from the stars might just be the energy to preserve our own world. Building an entire economy in space requires more than just a blueprint. It demands a fundamental rethinking of logistics. Every gram of water, every sheet of metal, every breath of air currently must be launched from Earth at staggering cost, a burden that grows heavier with every new project we envision. To break this costly chain, we must learn to use what the universe has already provided. Our third megastructure is the ultimate tool for this new era of cosmic self-sufficiency, a mass driver on the Moon. Picture not a rocket with fiery plumes, but a long, silent track laid across the barren lunar plains. This is an electromagnetic launch system, a kind of railgun that uses powerful magnetic fields to accelerate a cargo capsule along its length. In the Moon's gentle gravity, 1/6 of Earth's, and with no atmosphere to create drag or heat, this system can achieve something revolutionary. It can hurl raw materials directly off the lunar surface and into a stable orbit, or even onto precise trajectories toward other destinations, using only a fraction of the energy a traditional rocket would require. The cargo itself is the very ground beneath its tracks, processed lunar soil or regolith. This gray, dusty material is far more valuable than it appears. It can be processed to extract vital water ice from permanently shadowed craters, breathable oxygen for life support, and metals for construction. The mass driver transforms these extracted resources into readily available supplies. Instead of launching a 1,000-ton water tank from Earth, a single mass driver could launch a stream of standardized, water-filled containers from the Moon every day, creating a steady, affordable supply chain to orbital depots. This turns our celestial neighbor into the solar system's first off-world gas station and hardware store. The implications are profound for every structure we have discussed so far. The Lunar Gateway could be resupplied from a local source. Those vast orbital solar power satellites could be built from lunar metals, launched cheaply into space. Future missions to Mars could refuel their deep space vehicles from lunar depots, cutting the mass they need to lift from Earth in half. The mass driver is more than a piece of machinery. It is the foundational technology for in situ resource utilization, the practice of living off the land beyond our planet. It represents the moment we stop being visitors in space, hauling everything with us in a suitcase, and start becoming residents, learning to use the local resources to build a permanent home. This shift is the single greatest economic lever for our spacefaring future, and it begins with a silent, magnetic track on the silent Moon, catapulting our ambitions into the void. The silent efficiency of a lunar mass driver solves the problem of moving raw materials, but what about the people? Transporting human beings across the vast gulf between planets presents an entirely different set of challenges, ones of time, safety, and enduring comfort. The solution may not be a faster ship, but a smarter route. Imagine a permanent highway in the sky, a spacecraft that never lands, endlessly cycling between Earth and Mars on a predictable, gravitational freeway. This is the Mars Cycler, a concept that transforms interplanetary travel from a series of isolated, perilous expeditions into a routine, sustainable commute. The core idea is elegant in its simplicity. Once a large, well-shielded vessel is placed on a carefully calculated orbit that uses the gravity of Earth and Mars like gravitational slingshots, it will forever loop between the two planets on a repeating schedule, perhaps every 2 years when their orbits align. This cycler ship itself becomes the permanent habitation module for the long journey. Smaller, efficient taxi craft, launched from each planet, would only need to carry passengers and fresh supplies to rendezvous with this passing cosmic bus, dock with it, and then later detach to land at their destination. The cycler never slows down to enter an atmosphere or orbit, conserving a tremendous amount of fuel and complexity. The true revolution, however, happens inside. A months-long journey in a cramped, zero-gravity capsule is a severe hardship on the human body, leading to muscle atrophy, bone density loss, and other health risks. The Mars Cycler is designed as a true vessel for life, not just transport. Its most critical feature is the ability to generate artificial gravity through slow rotation, creating a comfortable, familiar environment where crews can live, work, and exercise normally. Thick shielding, potentially using water or other materials, would protect inhabitants from the relentless cosmic radiation of deep space. This transforms the psychology of the journey entirely, from a risky, austere mission into a manageable segment of a larger life, complete with private quarters, communal areas, and even gardens. Establishing such a system would be the crowning achievement of interplanetary logistics. It creates a predictable, reusable backbone for the entire Martian colonization effort. Settlers could plan their emigration years in advance, knowing exactly when the next cycler would arrive. Critical machinery, medical supplies, and cultural goods could flow regularly between the planets, fostering a true economic and social connection rather than a tenuous lifeline. The perilous expedition of legend becomes the reliable commute of a new generation. the essential infrastructure that turns a distant outpost into a thriving branch of human civilization, forever linked to home by a highway that moves among the stars. The promise of a self-funding space economy hinges on a simple, powerful idea: turning raw cosmic materials into usable wealth. This brings us to the fifth megastructure, an asteroid mining outpost, a concept that redefines the very purpose of leaving our planet. For centuries, we have seen asteroids as distant, inert rocks, occasional threats from the void, or subjects of scientific curiosity. But a new perspective is emerging, one that views them as untapped reservoirs of immense value, the ore bodies and fuel tanks of the solar system, waiting in the gravity well of space. Near-Earth asteroids, those that pass relatively close to our orbit, are not all the same. Some are rich in precious metals like platinum, iridium, and palladium, materials essential for advanced electronics, medical devices, and clean energy technologies on Earth. Others, often called carbonaceous or icy asteroids, hold vast quantities of water ice and volatile compounds like ammonia and methane. This simple water is the most transformative resource of all because it can be split into liquid hydrogen and liquid oxygen, the fundamental components of the most powerful rocket propellants we use. An asteroid mining outpost would be humanity's first dedicated industrial facility beyond the Moon, a fully operational base established either on the surface of a suitable asteroid or in a stable orbit nearby. The operation would be a symphony of automation. Robotic prospectors would first map and core sample the asteroid, identifying the richest veins of material. Then autonomous miners, perhaps using focused solar mirrors to gently heat and fracture rock, or mechanical drills designed for microgravity, would begin the extraction process. The raw ore wouldn't be shipped back to Earth in bulk. That would be far too energy-intensive. Instead, the outpost would include sophisticated, compact processing plants. These facilities would use techniques like magnetic separation or heating to distill the asteroid material on site, separating pure water ice from regolith and extracting concentrated metal nuggets. The output is a portfolio of high-value products. The platinum group metals could be launched toward Earth in dense, shielded capsules for recovery, supplying global industry without the immense environmental and social cost of terrestrial mining. The water, however, would stay in space. It would be electrolyzed into hydrogen and oxygen and stored in massive, orbiting fuel depots. These depots become the critical infrastructure for everything else we want to build. A spacecraft heading to Mars could launch from Earth with mostly empty tanks, a much lighter and cheaper proposition, and then refuel at one of these asteroid-supplied depots before embarking on its interplanetary journey. This completely changes the economics of deep space travel. To oversee and maintain this complex ballet of machines, a small crew would live in a connected habitat module. Their role isn't manual labor in the traditional sense, but high-level supervision, repair, and quality control, ensuring the robotic systems function smoothly. Their presence turns the outpost from a remote automated factory into a true foothold, a place where human judgment and adaptability are integrated into an off-world industrial process. The success of a single, profitable asteroid mining outpost would send a shockwave through the global economy. It would prove unequivocally that space is not just a realm of exploration and discovery, but one of tangible, extraordinary commerce. The potential value of a single medium-sized metallic asteroid is estimated to be in the trillions of dollars. Capturing even a fraction of that value could fund the next wave of space development, creating a virtuous cycle where the profits from one venture pay for the next leap forward. This outpost does more than extract resources. It transforms our entire relationship with the cosmos. It turns asteroids from mere celestial objects into strategic assets, proving that humanity can not only visit space, but can work there, prosper there, and use its infinite resources to build a future that benefits both Earth and the stars. While asteroid mining provides the raw materials and economic fuel, it begs a larger question: what is all this industry ultimately for? The sixth megastructure on our list provides the most profound answer: a place not just to work but to live a full human life. The O'Neill Cylinder Space Colony moves us beyond outposts and stations into the realm of true settlement, the creation of permanent, Earth-like worlds built by human hands. The vision, first detailed by physicist Gerard O'Neill in the 1970s, is both staggering in scale and elegantly simple in principle. Picture two immense cylinders, each perhaps 32 kilometers long and 8 kilometers in diameter, rotating slowly in opposite directions to cancel out gyroscopic effects. They are connected at their ends by a central hub and float together in the stable gravitational parking lot of a Lagrange point, a place where the pulls of Earth and the Sun balance perfectly. It is inside these spinning drums that the miracle happens. The entire inner surface of each cylinder becomes a living landscape, held against the wall by centrifugal force, which creates a comfortable Earth-normal gravity for everyone standing within. The scale is difficult to grasp, but imagine a valley so vast its curve is barely perceptible, a strip of land longer than the island of Manhattan and several kilometers wide, wrapped into a circle. Along this entire interior, you could have rolling hills, forests, rivers, towns, and farmland, all under a vast, arched ceiling of windows running the length of the cylinder. This is not a sealed metal can, it is a contained sky. Sunlight is directed into the colony via massive, adjustable mirrors orbiting outside the structure. By tilting these mirrors, the colony's administrators can simulate a perfect 24-hour day-night cycle, with dawn, daylight, dusk, and a starry night, all controlled with the flick of a switch. The climate would be carefully regulated, creating eternal spring, free from hurricanes, droughts, or blizzards. The entire structure is encased in a thick shell of lunar regolith or asteroid slag, providing a natural shield against cosmic rays and micrometeorites, making the interior environment potentially safer from space radiation than living on the surface of Mars. This is the crucial leap from surviving in space to thriving in it. An O'Neill cylinder is designed as a complete, closed ecological system. Water and air are endlessly recycled. Food is grown in rich, controlled agricultural belts. It is a world built for generations, where children are born, where communities establish their own cultures, and where life unfolds with a sense of normalcy impossible in a cramped orbital module or a dusty planetary habitat. The social and psychological impact of this cannot be overstated. For the first time, living off Earth would not mean enduring a prolonged camping trip under extreme duress. It would mean moving to a new hometown with its own unique beauty and opportunities. Construction, while monumental, follows a logical progression from the infrastructure we've already discussed. The metals and minerals would come from asteroid mines. The bulk shielding material could be launched from the moon using mass drivers. The assembly would be undertaken by armies of automated construction robots, building the colossal framework piece by piece in the airless quiet of space. The first cylinder might take decades to complete, but it would establish the template, and subsequent colonies could be built faster as our experience grows. The emergence of such colonies would represent a fundamental branching point for humanity. They offer a powerful answer to existential risks, ensuring that our species' future is not tied to a single planet. They provide living space without further taxing Earth's biosphere, and perhaps most importantly, they restore a sense of cosmic optimism, a tangible demonstration that our future among the stars can be one of abundance, beauty, and hope, a place where the human story continues, not just endures. This vision of a manufactured paradise brings us to a more immediate and gritty challenge, however, one that must be solved long before we can build such serene worlds. How do we protect these fragile human habitats and the spacecraft traveling between them from the most relentless danger in the void, radiation? Yet the serene promise of orbital colonies rests upon solving a far more immediate and gritty challenge: the relentless, invisible rain of cosmic radiation. Shielding entire rotating worlds is one thing, but protecting the fragile spacecraft and their human cargo traveling between them demands a different kind of megastructure, one that redefines the very concept of a launch pad. The seventh megastructure on our list is perhaps the most audacious engineering concept ever conceived for Earth: a space elevator. This is not a tower built upward from the ground, but a ribbon, a tether of unimaginable strength, stretching from the surface of our planet straight up into the heavens. One end is anchored to a massive platform at the equator, likely floating on the ocean. The other end extends far beyond geostationary orbit, 36,000 kilometers high, where it connects to a colossal counterweight, perhaps a captured asteroid or a purpose-built station. This entire system rotates with the Earth, holding the ribbon taut through centrifugal force, creating a permanent, stable bridge to space. The principle is elegantly simple. Instead of fighting Earth's gravity with explosive rocket thrust, we would simply ride up. Automated climbers, powered by lasers or microwaves from the ground, would ascend this ribbon like electric trains on a vertical track, carrying cargo and eventually passengers into orbit. The economic transformation would be nothing short of revolutionary. Current rocket launches cost thousands of dollars per kilogram to reach orbit. A mature space elevator could slash that cost by over 90%. Turning orbital access from a rare, expensive event into a routine, affordable logistical operation, akin to loading a container ship. This changes everything. The primary obstacle has always been material science. The ribbon must be incredibly strong yet astonishingly light to support its own immense weight and the stresses of the climbers. For decades, this seemed like an impossible requirement. But the key may lie in the microscopic realm of carbon nanotubes, theoretical threads of carbon atoms arranged in a perfect hexagonal lattice. Laboratory experiments have shown that individual nanotubes possess the necessary tensile strength, hundreds of times stronger than steel at a fraction of the weight. The challenge for this century is scaling that microscopic perfection up to a macro scale, manufacturing thousands of kilometers of flawless, defect-free ribbon. Researchers around the world are making incremental progress, developing new composite materials and manufacturing techniques that inch us closer to this goal. If and when this material hurdle is overcome, the construction process itself would be a marvel. The initial seed ribbon, thinner than a pencil lead, would be launched to geostationary orbit and slowly unspooled downward toward the ocean and upward toward the counterweight simultaneously, growing stronger and wider with each subsequent climber that ascends, adding more strands to the structure. The completion of a space elevator would act as the ultimate economic catalyst for every other project we have discussed. Suddenly, launching the massive components for orbital solar power satellites becomes trivial. The raw materials mined from asteroids can be delivered to Earth orbit with minimal energy cost. Building the O'Neill cylinders shifts from a centuries-long endeavor to a project with a conceivable timeline. It demystifies space, turning it from a hostile frontier into an accessible high ground, a place where industry and community can flourish because the cost of getting there and back is no longer a prohibitive barrier. It would open the floodgates, making the vision of a bustling, interconnected spacefaring civilization not just possible, but economically inevitable. While a space elevator revolutionizes access from Earth, our ambitions stretch far beyond our home world. The Martian system presents its own unique set of logistical puzzles, demanding infrastructure tailored to its alien environment. The eighth megastructure on our list offers a brilliant solution, not on the red planet itself, but anchored to its enigmatic moons, A permanent space station on Phobos or Deimos would become the ultimate strategic command post for the conquest of Mars. These small, potato-shaped moons are not mere rocks to be passed by. They are ready-made platforms with extraordinary advantages. Their gravity is so faint it is almost non-existent, a fraction of a percent of Earth's. This makes landing spacecraft on them and launching back into space an operation requiring minimal fuel, a stark contrast to the energy-intensive process of descending into and lifting off from Mars's deeper gravity well. This alone transforms them into the perfect interplanetary truck stops, but they are far more than just convenient parking lots. Scientific data strongly suggests both moons, particularly Phobos, contain significant reserves of water ice and other volatile materials buried beneath their dusty surfaces. A station anchored here could deploy robotic miners to extract this water, processing it into hydrogen and oxygen rocket fuel right at the orbital gateway. Imagine a Mars-bound ship arriving from Earth. Instead of carrying all the fuel needed for its return journey, which is immensely heavy, it could dock at the Phobos station, refill its tanks with locally produced propellant, and then descend to the Martian surface with a much lighter load. When the crew is ready to come home, they would launch a smaller ascent vehicle just to reach the waiting station, refuel again, and begin the journey back to Earth. This breaks the monumental challenge of a Mars mission into smaller, more manageable, and far more economical steps. The station's location offers another profound benefit: a permanent, unblinking eye over the entire Martian sphere of operations. Shielded within the bulk of the moon itself, the station would be protected from solar radiation and micrometeorites. From this safe haven, crews could teleoperate vast swarms of drones and robots on the Martian surface with almost no signal delay, building bases, conducting research, and maintaining equipment in real time. It becomes the orbital nerve center, a place where mission planners, scientists, and engineers live and work while directly managing the day-to-day activities on the planet below. This avoids the need for continuous, risky surface landings for every new task or crew rotation. The station would naturally evolve into a bustling shipyard and service depot, where interplanetary vessels are assembled, maintained, and prepared for their next voyages deeper into the solar system. By establishing this foothold on the moon's first, we don't just visit Mars, we gain permanent, sustainable control over its entire environment. The Phobos or Deimos station is the master key that unlocks the Martian frontier, turning a distant dream of colonization into a streamlined, operational reality. But our ambitions will never be satisfied with the confines of our own solar system. The 9th megastructure on our list is not a place for us to live, but a message in a bottle for the cosmos, a project designed to answer the oldest question of all: are we alone? The Breakthrough Starshot initiative is a radical reimagining of interstellar travel. Its goal is not to send a single, heroic vessel on a journey lasting millennia, but to dispatch a swarm of tiny, gram-scale probes to our nearest stellar neighbor, the Alpha Centauri system, and have them arrive within a single human lifetime. The core concept turns traditional rocket science on its head. Instead of carrying massive fuel tanks, each tiny probe, no larger than a postage stamp, would be equipped with an ultra-thin, highly reflective light sail. The propulsion would come not from onboard engines, but from a colossal array of powerful ground-based lasers, focused into a single, coherent beam spanning kilometers in diameter. This laser array, a fixed installation of immense scale and precision, is the true megastructure of the project. It would act as a cosmic slingshot, bathing the delicate light sails in an intense push of pure energy, accelerating the fleet to an almost inconceivable velocity, 20% the speed of light. At that pace, the 4.37 light-year journey to Alpha Centauri would take just about 20 years. The engineering challenges are, of course, monumental. Each nanocraft must survive the blistering acceleration, the decades-long cruise through the interstellar void bombarded by cosmic dust, and then successfully operate upon arrival. They would need microscopic cameras, sensors, and communication systems, all hardened against radiation and functioning on minimal power. The plan is for the swarm to sail past any planets in the system at this tremendous speed, snapping images and collecting data in a fleeting flyby, then beaming that precious information back to Earth using tiny lasers, a signal that would take over 4 years to reach us. While each individual probe is a miniature marvel, the true achievement lies in the supporting infrastructure. Constructing and coordinating that kilometers-wide laser array represents a peaceful, global undertaking of unprecedented optical and electrical engineering. It is a monument not to empire but to pure, shared curiosity. The data returned, even if just a handful of pixels showing the disk of an exoplanet, would revolutionize our understanding of the universe. It would tell us about the conditions around another star, offer clues about the potential for life elsewhere, and finally give us a close-up view of worlds that have lived only in our telescopes and our dreams. Breakthrough Starshot embodies a profound philosophical shift. It accepts that sending humans between the stars may remain out of reach for centuries, but it refuses to let that limit our exploration. By leveraging the twin powers of light and miniaturization, it seeks to extend our senses across the interstellar gulf within the span of a single career. This project, more than any other, is a statement of intent for our species. It says that our curiosity is boundless, that we are determined to know our neighbors, and that our first step into the galactic community begins not with a giant leap, but with a whisper-thin sail pushed by a beam of light from home. Venus stands as a stark warning of a runaway greenhouse effect, its surface hot enough to melt lead under crushing atmospheric pressure. Yet, high above this inferno lies a startling oasis, a layer in the Venusian sky that may offer the most Earth-like environment in our entire solar system. This brings us to our 10th megastructure, the Venusian Cloud City, a vision that turns planetary science into a breathtaking architectural principle. At an altitude of approximately 50 kilometers, the atmospheric pressure is nearly the same as we experience at sea level on Earth, and the temperature ranges from a comfortable 30 to 80 degrees Fahrenheit. Instead of battling the hostile surface, this concept proposes we simply float above it all. The city itself would be a vast, interconnected network of pressurized habitats, not anchored to the ground but buoyant, held aloft like a fleet of titanic, intelligent balloons. Each habitat envelope would be filled with a breathable mixture of oxygen and nitrogen, which is significantly lighter than the thick carbon dioxide atmosphere of Venus, providing natural lift. The entire structure would drift gracefully in this temperate zone, navigating the gentle wind currents that circle the planet. Life in the Cloud City would be defined by its unique relationship with the environment. Solar power is abundant above the reflective cloud decks, providing limitless energy. The atmosphere itself becomes a primary resource, an almost infinite supply of carbon dioxide that could be processed into breathable oxygen for the inhabitants and carbon for manufacturing materials. Imagine vast, semi-transparent processing facilities suspended alongside the living quarters, quietly turning the poisonous air into the very building blocks of civilization. Access to the surface for robotic mining of minerals would be possible via heavily shielded elevator systems or autonomous drones, but the city's primary existence would be aerial, a serene archipelago in a golden sky. This is not a retreat from a challenge, but a masterclass in adaptive engineering. It expands our definition of a planetary habitat, proving that a world does not need a solid, welcoming surface to become a home. It teaches us to look beyond the obvious, to find the narrow band of possibility within an otherwise forbidding environment. A successful cloud city would stand as a monument to human ingenuity, a permanent settlement not on a world, but within its sky, forever floating in the gentle light between the hell below and the cold void above. This elegant solution for Venus prepares our thinking for an even greater environmental transformation, one where we wouldn't just adapt to a world, but would actively reshape it into something new. The extreme environments of other worlds force us to rethink where a home can be. Yet sometimes the most ingenious solution is not to build something new, but to discover what the cosmos has already constructed for us. Beneath the barren, gray plains of the Moon lies a hidden network of colossal caverns, the legacy of its volcanic past. These are lunar lava tubes, formed when the outer surface of a molten lava river cooled and solidified, while the interior lava drained away, leaving behind a hollow, tunnel-like void. On Earth, such tubes are mere curiosities, perhaps large enough to walk through. On the Moon, with its weaker gravity and different volcanic history, they are titanic. Radar scans and images of gaping pit entrances suggest some of these subsurface tunnels could be hundreds of meters wide and stretch for kilometers, vast enough to contain entire city skylines. This natural architecture presents an extraordinary opportunity. The 11th megastructure on our list is not something we launch from Earth, but something we move into, a lunar lava tube base. The advantages are profound and address the three greatest threats to long-term lunar living. The overhead rock, often tens of meters thick, provides a perfect shield against cosmic radiation and solar flares, dangers that would require complex and heavy artificial shielding for any surface dome. It also serves as a barrier against the constant, high-velocity rain of micrometeorites that have pitted the lunar surface for eons. Finally, it insulates against the Moon's brutal temperature swings, where surface temperatures can soar to 260 degrees Fahrenheit in sunlight and plunge to 280 degrees below zero in the darkness of night. Inside a sealed tube, the environment could be maintained at a stable, comfortable temperature year-round. The process of turning a cave into a city begins with robotic scouts mapping the tube's full extent and structural integrity. Once a stable section is identified, the next step is to create an airtight seal at one or both ends, perhaps using an inflatable membrane anchored to the rock walls and then reinforced with a spray of molten regolith, a building material made from the Moon's own soil. After sealing, the entire colossal volume could be slowly pressurized with a breathable atmosphere. The result is instant, immense, prefabricated real estate. Instead of painstakingly assembling cramped habitats on the dangerous surface, we inherit a grand, cathedral-like space. Within this protected underground realm, a true city could take shape. Vast open areas could be dedicated to vertical farming, using carefully tuned artificial light to grow food for thousands. Industrial zones could house factories that process lunar regolith into metals, glass, and oxygen, their operations contained and safe. Residential districts with multi-level structures built along the cavern walls could offer views of internal parks and water features, all under the gentle, artificial glow of a simulated sky projected onto the cavern ceiling. This approach represents a fundamental shift in our philosophy of expansion. We are not conquering a hostile landscape through sheer force of engineering. We are adapting to it, using its own geological gifts to secure our foothold. A lava tube base leverages the Moon's greatest resource, its geology, to solve the hardest problems of space habitation. It allows for rapid, scalable growth of a permanent lunar civilization, where the primary construction work is modification, not creation from scratch. This turns a silent, empty tunnel, a relic of the Moon's fiery youth, into the bustling main street of humanity's first off-world metropolis, a testament to living wisely with the universe we find. A thriving civilization across multiple worlds requires more than ships and stations. It needs a voice. The 12th megastructure on our list is not a physical habitat or a power plant, but something equally vital, the invisible nervous system that will connect it all, a solar system-wide internet constellation. As our presence expands from the Moon to Mars and beyond, the simple act of sending a message or a data packet becomes a monumental challenge of physics. Relying on direct links to Earth would create intolerable delays, up to 40 minutes round trip with Mars at its farthest, making real-time conversation or remote control of machinery impossible. The solution is to weave a web of light throughout the inner solar system. This network would consist of a constellation of sophisticated relay satellites, positioned at strategic gravitational anchor points like Lagrange points and in stable orbits around the Sun, Mars, and other key destinations. Each node acts as a celestial router, receiving a laser beam signal from one point and precisely redirecting it to the next, creating a continuous high-bandwidth data highway. Building this system would be an incremental, relentless process, mirroring the expansion it is designed to serve. The first links would establish a reliable backbone between Earth and the Lunar Gateway. Then, as crewed missions head to Mars, relay satellites would be prepositioned along the transfer orbit, ensuring the spacecraft never loses its high-speed link to home. Eventually, a permanent constellation around Mars itself would link orbiting stations, surface bases, and robotic explorers into a seamless local network, which then connects back to Earth via the interplanetary trunk line. The bandwidth enabled by laser communication is staggering, capable of transmitting high-definition video, vast scientific datasets, and even the collective cultural output of an off-world colony without a perceptible lag within local networks. This transforms the experience of living on another world. A student in an O'Neill cylinder could take a virtual reality field trip to the Martian canyons in real time, guided by a scientist actually standing there. A doctor on Earth could consult on a medical procedure at a lunar base, watching the robotic instruments move as if they were in the same room. Families separated by hundreds of millions of kilometers could share a meal over a video call with only the light delay of physics, not one imposed by inadequate technology. This digital infrastructure does more than move information. It maintains the social and psychological fabric of a scattered civilization. It ensures that a new discovery on Titan is known instantly in laboratories on Earth, that a political decision made by a Martian council is communicated clearly and without distortion, and that the art and stories created in deep space become part of humanity's shared heritage. The interplanetary internet is the ultimate tool against isolation, the guarantee that as we venture outward, we do not fragment into disconnected tribes, but grow as a single, interconnected community bound by the speed of light. It is the silent, constant hum of consciousness that turns a collection of outposts into a true interplanetary society. This web of connection would also oversee the most ambitious engineering project of all, one that doesn't just use a world but actively heals it. The interplanetary internet weaves a web of consciousness, but to act upon that knowledge we need vessels. The 13th megastructure on our list is the ultimate deep space factory, a Ceres orbital shipyard. Far beyond Mars, nestled within the asteroid belt, orbits the dwarf planet Ceres, a world that holds a secret of immense value for our expansion. Scientific observations from visiting probes have confirmed that Ceres possesses vast subsurface reservoirs of water ice, likely mixed with other volatile compounds like ammonia and methane. This simple fact transforms this distant, rocky body from a scientific curiosity into the most strategic real estate in the outer solar system. Water is the oil of spacefaring civilization, the source of life support, and when split into hydrogen and oxygen, the most powerful rocket propellant we know. Establishing a massive shipyard in orbit around Ceres is about building where the fuel already is. The concept leverages two powerful advantages. First, constructing large spacecraft in the microgravity environment of orbit is fundamentally easier than on any planetary surface. There is no gravity well to fight during assembly, allowing for the creation of delicate, expansive structures that could never launch from Earth or Mars, things like enormous fuel tanks, gossamer thin solar sails, or the rotating habitats for multi-year journeys. Second, Ceres itself becomes the supply depot. Robotic miners on its surface would extract the water ice, which would then be launched via mass drivers or processed locally and lifted to the orbital yard. There, automated factories would electrolyze it into cryogenic fuel, filling the tanks of the very ships being assembled nearby. This creates a perfect, closed industrial loop. The shipyard would be a sprawling complex of interconnected modules, a symphony of coordinated robotics. One section would fabricate structural beams from metals harvested from nearby metallic asteroids. Another would spin and weave carbon composites into hull plating. A third would consist of vast, insulated tanks for fuel storage, constantly replenished from the surface operations below. The vessels born here would be of a class unimaginable for Earth launch, colossal freighters designed to haul thousands of tons of cargo between the asteroid belt and the inner planets, or specialized science platforms built to explore the icy moons of Jupiter and Saturn. Most significantly, this is where the first true generation ships, vessels designed for multi-century voyages to other stars, could feasibly be constructed, their immense frameworks assembled in the gentle embrace of microgravity. This transformation is profound. The Ceres orbital shipyard turns the asteroid belt from a distant, mineral-rich frontier into the industrial heartland of a mature spacefaring culture. It becomes the Detroit of deep space, the place where the vehicles for the next great phase of exploration are forged not from terrestrial resources, but from the very fabric of the cosmos itself. It marks the point where humanity's reach truly extends throughout its stellar neighborhood, powered and built from the materials found along the way. This bustling network of commerce and communication creates a new kind of vulnerability. The very orbits that host our future are already littered with the silent, high-speed shrapnel of our past, a growing cloud of defunct satellites and collision fragments. Our 14th megastructure is not about expansion, but about preservation, a global orbital defense and debris removal system. This is the essential maintenance crew for the final frontier, a constellation of specialized servicer satellites with a clear mandate to ensure the highways of space remain open and safe for everyone. Each servicer is a multi-tool for orbital stewardship. Some are designed as nimble inspectors, equipped with advanced sensors and robotic arms to rendezvous with aging satellites, diagnose malfunctions, and perform delicate repairs, extending the life of vital assets. Others function as orbital tankers, docking with communication or observation satellites to replenish their fuel, allowing them to maintain their precise positions for decades longer. The most critical function, however, is active debris removal. These servicers would track down derelict rocket bodies and shattered fragments, capture them using nets, harpoons, or robotic grippers, and then safely guide them on a controlled descent to burn up in Earth's atmosphere. This proactive cleaning is not optional. It is an absolute necessity to prevent a cascade of collisions known as Kessler syndrome, where one impact creates thousands of new fragments, each capable of causing more destruction, potentially rendering entire orbits unusable for generations. To address natural threats, some elements of the network might incorporate limited defensive capabilities, not as weapons but as shields. These could involve sensors to track small, natural micrometeoroid swarms and the ability to maneuver valuable assets out of harm's way, or even test technologies to gently nudge such natural debris onto safer paths. The goal is comprehensive space traffic management and environmental protection. The value this system protects is astronomical. The trillion-dollar space economy of satellite communications, Earth observation, scientific research, and the foundational platforms like the Gateway and Future Power satellites. Without it, a single piece of untracked debris could sever the digital lifelines of modern civilization or cripple the infrastructure we are counting on for our future. Building and operating this coordinated fleet represents a profound shift in our relationship with near-Earth space. It moves us from being mere visitors who leave trash behind to becoming permanent, responsible stewards. It proves that we can not only build grand structures among the stars, but that we have the wisdom and the technology to care for that domain, to keep it secure and sustainable for all the endeavors that will follow. This commitment to stewardship naturally extends to worlds beyond our own, where we may undertake the ultimate act of planetary care. The silent, automated guardians of Earth orbit ensure our celestial infrastructure remains secure, but the greatest discoveries often lie in the most alien environments. Far beyond the asteroid belt, under the orange haze of a thick nitrogen sky, another world holds a liquid secret. Saturn's moon Titan is a place of profound and eerie familiarity, with rolling dunes, river valleys, and vast calm seas. Yet these are not seas of water, but of liquid methane and ethane, flowing at temperatures hundreds of degrees below zero. To navigate this frigid, organic soup, we would not send a rover but a submarine. The 15th Megastructure is a nuclear-powered Titan submarine explorer, a vessel designed for a voyage unlike any other in human history. This would not be a simple probe, but a sophisticated, autonomous laboratory built for endurance in an utterly alien ocean. Powered by a compact radioisotope thermoelectric generator, it could operate for years, descending into the in-kai depths of Kraken Mare or Ligeia Mare, seas larger than North America's Great Lakes. Its mission would be twofold, and each goal is revolutionary. First, it would study the complex probiotic chemistry at work. Titan's methane cycle mimics Earth's water cycle, with evaporation, clouds, rain, and rivers, but with organic molecules as the working fluid. The submarine would sample this primordial soup directly, analyzing the complex hydrocarbons that swirl in the dark to understand the chemical steps that may have led to life on Earth. Second, and more profound, it would search for signs of exotic life itself, organisms that might use liquid methane as a solvent instead of water, breathing hydrogen and consuming acetylene. Finding even simple life here would prove that biology is not a singular miracle of Earth, but a common, adaptable process in the universe. While the submarine itself is a single vehicle, its operation constitutes a true megastructure of exploration due to the immense support network required. A dedicated orbiter around Saturn would act as a crucial communications relay, catching the submarine's data packets and beaming them across the billion-mile gulf back to Earth. A lander or floating platform on Titan's shore might serve as a docking and service station, allowing the submarine to periodically surface, transfer its full data loads, and potentially receive software updates, or even have its samples collected for a future return mission. This creates an integrated, multi-element architecture focused on a single, extraordinary goal. The engineering challenges are as vast as the seas it would sail. The submarine must be exceptionally buoyant, as liquid methane is less dense than water. Its cameras and sensors must peer through a dark, potentially particle-filled haze. Every moving part, every seal, must function flawlessly in cryogenic temperatures that make metals brittle and lubricants freeze. Yet, these are problems with solutions grounded in known physics and material science. Sending such a vessel represents the pinnacle of robotic exploration, a leap from mapping surfaces to plumbing the depths of another world's active hydrosphere, or rather, methanosphere. The data returned would do more than fill textbooks. It would fundamentally expand our concept of a habitable zone and the very conditions necessary for life to arise. A successful mission to Titan's seas would teach us not only about a distant moon, but about the resilience and creativity of nature itself, suggesting that wherever there is energy, liquid, and organic chemistry, the spark of life might find a way. This search for life in an alien ocean prepares us for a more profound and permanent transformation, one where we move beyond exploration to actively nurture a new world. Mercury stands as the sentinel of the inner solar system, a world scorched and scoured by the raw power of its parent star. Yet within this furnace of a planet lies a paradox of immense value, a combination of resources that could transform it from a barren rock into a powerhouse of both energy and discovery. The 16th megastructure on our list is a Mercury solar power and research base, a facility that would turn the planet's greatest challenges into its most profound assets. The logic begins with simple physics. Orbiting so close to the Sun, Mercury receives almost 7 times more solar energy per square meter than Earth does. This makes its sunward side an ideal location for solar farms of staggering efficiency, using advanced photovoltaic panels or even solar thermal systems that focus the intense light to generate immense heat for power production. But the surface temperature there is far too extreme for sustained human activity or delicate machinery. The solution lies in a clever piece of celestial geography, the planet's polar regions. Due to Mercury's minimal axial tilt, the floors of certain craters at its poles are in permanent, deep shadow, creating cold traps where water ice delivered by comets over billions of years has accumulated and remained frozen. This is the key that unlocks the entire concept. A base would be established within or adjacent to these shadowed craters, using the ice as a source of water for life support and fuel production, while the sunlit crater rims just kilometers away become the sites for those massive solar arrays. The base itself, nestled in perpetual darkness and coolness, would be a shielded haven protected from the blistering heat and radiation. From this unique vantage point, Mercury becomes a premier platform for science. Telescopes placed on the planet's night side, or even within the shadowed craters, would operate in an environment of profound darkness and stability, offering crystal-clear views of the universe unobstructed by an atmosphere. But the primary target would be the Sun itself. A Mercury-based solar observatory could study our star's corona, solar flares, and magnetic activity with unprecedented detail and continuity, providing early warnings for solar storms that could threaten Earth's power grids and space assets. The intense, constant solar energy also enables experiments impossible anywhere else, such as testing advanced materials under extreme flux or piloting industrial processes that require phenomenal amounts of heat. The power generated would be truly colossal, far beyond the needs of the local base. This surplus opens another fascinating possibility, beaming that energy to other locations. While beaming power directly to Earth across such a distance presents immense technical hurdles, it could be a viable source for spacecraft operating in the inner solar system or for future outposts on the Moon or Venus, creating a strategic energy hub. This megastructure represents the pinnacle of adaptive engineering. It does not fight Mercury's environment. It meticulously navigates its extremes, using the cold of eternal shadow to support life while harnessing the fury of perpetual sunlight to fuel ambition. A successful base on Mercury would be the ultimate demonstration of our species' resilience and ingenuity, proving that no corner of our star system, no matter how initially hostile, is beyond the reach of a thoughtful, resourceful civilization. It turns the doorstep of the Sun from a no-man's land into a beacon of knowledge and power. The quest for life cannot be satisfied with mere observation from a distance. It demands we go to the water. Orbiting Jupiter, the moon Europa glimmers with a promise locked away beneath a shell of ice kilometers thick, a global saltwater ocean that may hold more liquid water than all of Earth's seas combined. Our 17th megastructure is a dedicated mission of profound ambition, the Europa ice-penetrating orbiter and base, a multi-element architecture designed not just to visit this world, but to literally dive into its hidden heart. This is not a single spacecraft, but an entire ecosystem of technology working in concert to achieve what no mission has ever attempted: to directly probe an alien ocean. The journey begins with a powerful orbital platform, a sentinel that would circle Europa with a singular focus. Its most critical instrument would be an advanced radar system, far more powerful than any flown before, designed to map the ice shell's thickness, structure, and to pinpoint the most promising locations for descent, places where the ice might be thinner or where subsurface lakes might press up against the underside of the crust. This orbiter is more than a cartographer, however. It becomes the permanent communication hub, the vital link that relays every precious bit of data from the surface operations back across the vast gulf to Earth. It could also serve as a power station, beaming energy via laser or microwave to the surface base below, enabling long-term operations without relying solely on limited onboard generators. The true adventure begins at the chosen landing site, a heavily shielded surface base, likely nuclear-powered to survive in the intense radiation environment of Jupiter's magnetic field, would serve as the operations center and laboratory. Its primary task is to deploy the system's most daring component, a thermal probe, often called a cryobot. This device is essentially a robotic melting torch, using heat generated from a radioisotope source to slowly, methodically melt its way straight down through the kilometers of ice. As it descends, it would leave behind a communications tether, a thin fiber optic line connecting it back to the surface base, transmitting real-time data on the ice composition, temperature, and any signs of organic material it encounters along the way. The grand finale occurs when the cryobot finally breaches into the dark ocean below. Here, it would release one or more autonomous submersible drones, tiny, agile explorers built for a realm of perpetual night. These drones would be our eyes and hands in the abyss, equipped with cameras, chemical sensors, and samplers. They would navigate the currents, searching for hydrothermal vents on the ocean floor, places where energy and minerals could fuel ecosystems entirely separate from sunlight, much like those found in Earth's deepest trenches. They would taste the water, analyzing its chemistry for the building blocks of life, or even, against all odds, for the chemical signatures of living processes themselves. Every component, from the orbital relay to the surface station to the descending cryobot and its aquatic drones, forms an interconnected megastructure of discovery. Its sole purpose is to answer a question that has echoed through human history: are we alone? By seeking life in Europa's dark sea, we are testing a fundamental principle of the cosmos, that where there is liquid water, energy, and the right chemistry, life might be an inevitable, flourishing outcome. The data returned, whether it reveals a sterile sea or a world teeming with alien biology, would irrevocably change our understanding of our place in the universe. It would tell us if life is a rare, precious flame or a common spark waiting to be kindled in hidden oceans across the galaxy. This search for our cosmic siblings leads us to consider a future where we no longer merely search for life, but actively create new homes for it, transforming entire worlds through the most patient and powerful engineering of all. The profound search for life on Europa is a journey of pure science driven by our deepest questions, but the human drive to explore is also fueled by something simpler: a sense of wonder and the desire for a personal connection to the cosmos. This brings us to the 18th megastructure, a rotating space hotel for tourism. As the initial wave of suborbital joyrides matures, the next logical step is a destination, a place to stay and truly experience life off our planet. These will not be the cramped capsules of early space stations, but purpose-built habitats in low Earth orbit designed for comfort, leisure, and awe. The defining feature will be rotation, using centrifugal force to create sections of comfortable, Earth-like gravity, perhaps in a ring-shaped lounge or a dedicated gym area, allowing guests to move with ease after the novelty of weightlessness. Other sections would remain in microgravity for the classic floating experience, offering a playful contrast. The entire structure would be oriented to provide breathtaking, panoramic views of Earth rolling by below, a blue and white marble against the infinite black velvet of space, seen through vast, reinforced viewports or even transparent domes. These hotels represent the full commercialization and normalization of space habitation. Serviced by regular, reusable shuttle flights, they would make a short-term stay in orbit accessible not just to governments and billionaires, but eventually to a much broader segment of society, much like international travel evolved from a luxury for the few to an experience for the many. The business case is powerful, creating a consistent market that drives relentless innovation. To attract customers, these resorts will demand and fund major advances in closed-loop life support systems that are ultra-reliable and pleasant, in radiation shielding that is both effective and lightweight, and in space construction techniques that are fast and affordable. Every improvement tested here for comfort directly benefits the more critical habitats for scientists and settlers. Imagine the facilities, a fine dining restaurant where your fork floats away if you do not hold it, a viewing lounge for observing thunderstorms ripple across continents, or a recreational module for playing sports in 3 dimensions. This blend of high luxury and high frontier is precisely the point. These hotels are the resorts of the new frontier, blending leisure with a profoundly transformative personal experience. They answer a fundamental human yearning, not just to see a place, but to live in it, if only for a week. By creating a compelling, desirable reason for ordinary people to go to space, they generate the economic engine and public enthusiasm that accelerates our entire expansion. The tourist gazing out at the stars from a hotel balcony is participating in the same grand project as the scientist drilling into Europa's ice, each fueling the next great leap in their own essential way. This vision of accessible orbital living prepares us for a concept of staggering scale, one that moves beyond hotels and laboratories to reshape the fundamental relationship between a star and its planets. The bustling hotels of low Earth orbit offer a personal connection to space, but to understand our true place in the cosmos, we must journey to the silent frontier. Beyond the last of the planets, in the perpetual twilight of the Kuiper belt, lies the ultimate vantage point for astronomy, a realm of profound darkness and cold. Here, the sun is reduced to a mere brilliant star, and the background glow of the zodiacal light, the scattered sunlight from dust in the inner solar system, fades to near nothing. This is the perfect site for our 19th megastructure, a Kuiper Belt Observatory, a facility that would turn the frozen edge of our own solar system into the universe's grandest viewing platform. The concept leverages the unique environment of this distant region. Constructing a telescope here offers an advantage no Earth-based or even orbital observatory can match: the absence of light pollution in its most fundamental form. Freed from the glare of the sun and the inner system's dust, its instruments could peer into the depths of space with a clarity we have never known. But the genius of the design lies in its self-sufficiency. Rather than launching a fragile, pre-built telescope on a decades-long journey, the observatory would be constructed in place by autonomous robots, using the raw materials abundant in the belt itself. These robotic builders would harvest water ice from Kuiper belt objects to create massive, ultra-pure lenses or mirror blanks, and process local ices and rocky material for structural components. The resulting array could be built to a scale impossible within Earth's gravity, perhaps a network of linked telescopes spanning kilometers, acting as a single colossal eye. The scientific return would be revolutionary. With such a stable, dark platform, astronomers could study the atmospheres of exoplanets orbiting distant stars in unprecedented detail. analyzing their chemical compositions for signs of oxygen, methane, or other potential biosignatures with a precision that would settle the debate about life elsewhere. Closer to home, it would serve as a sentinel for our own solar system. From this distant perch, the observatory could systematically map the Oort cloud, that vast, theoretical shell of icy planetesimals that marks the true boundary of the Sun's influence. It could track long-period comets on their inward plunge centuries before they become visible from Earth, and keep watch for any unexpected, distant objects on trajectories that might one day bring them through the inner planets. This dual purpose makes it a megastructure of both profound discovery and prudent guardianship. It extends our vision to the faintest whispers of light from newborn galaxies, while simultaneously monitoring the dim, slow-moving traffic at our own cosmic doorstep. More than just a tool, a Kuiper Belt Observatory represents a philosophical milestone. It is a monument built not for commerce or colonization, but for pure, patient science. Its construction would signal that our drive to understand the universe is as powerful as our drive to inhabit it, that we value the questions as much as the answers. In the deep quiet of the outer dark, far from the warmth and noise of home, this silent array would stand as a testament to our endless curiosity, a lighthouse of consciousness gazing eternally outward, ensuring that as we build our future among the stars, we never lose sight of the infinite mystery that surrounds us. All these monumental structures, from lunar bases to interstellar probes, share a silent, driving question. Is there another world like ours? Our final megastructure offers the definitive answer, not through a single colossal instrument, but through an exquisite celestial dance. The Terrestrial Planet Finder Array is a fleet of formation-flying telescopes, a constellation of precision-crafted mirrors deployed into the deep, stable quiet of space far from Earth's interference. Individually, they are sophisticated observatories, but their true power emerges only in concert. Flying in a precise, choreographed formation separated by hundreds or even thousands of kilometers, they combine their light to function as a single, virtual telescope of unimaginable scale. This technique, called interferometry, allows them to achieve a resolution so sharp it could, from light years away, distinguish a planet from the overwhelming glare of its parent star. The engineering challenge is one of breathtaking exactitude. Each telescope must maintain its position relative to the others with nanometer precision, a distance less than the width of a single atom, while drifting in the void. They must align their collected starlight with perfect timing, a task requiring a network of lasers and atomic clocks to synchronize their observations across the vast emptiness between them. This orchestration of light and position is the megastructural achievement, a symphony of machines playing in perfect harmony across the solar system. The scientific payoff would be nothing less than historic. By precisely blocking the blinding light of a distant star, the array could directly image the faint, warm pinpricks of orbiting planets. But it would go far beyond mere pictures. By analyzing the thin sliver of starlight filtering through a planet's atmosphere, its spectrographs could detect the chemical fingerprints of water vapor, oxygen, methane, and other potential biosignatures. It would not just find another Earth-sized world. It could tell us if its air is breathable, if its cycles suggest liquid water, and if its chemistry hints at the delicate, persistent processes of life. This quest transforms the array from a tool of astronomy into a beacon of cosmic context. For all our ambition to build cities and highways among the stars, the most profound motivation has always been the search for company. Confirming the existence of a living world around another sun would provide the ultimate rationale for every structure on this list. It would give purpose to the shipyards at Ceres and the cyclers to Mars, framing them not as ends in themselves, but as the first, fledgling steps out of our cradle toward a galactic community we now know exists. The data streaming back from this silent fleet would answer the oldest human question whispered to the night sky, and in doing so, it would ignite the next great chapter of our story, providing a destination worthy of a journey that spans centuries. These 20 visions form a single, interdependent blueprint for our future. They are not isolated wonders, but the essential organs of a living, breathing spacefaring civilization, each one relying on the success of the others to function. The lunar mass driver provides the cheap materials needed to build the vast orbital solar power satellites. The limitless energy from those satellites then powers the robotic refineries at the asteroid mines. The metals and water harvested from those mines become the literal building blocks of the O'Neill cylinder colonies. Every connection reveals a deeper logic, a step-by-step progression where one achievement directly enables the next greater leap. This transforms a list of ideas into a coherent roadmap, a potential sequence for how humanity could logically expand its presence across the solar system. A realistic timeline for such an expansion stretches across the remainder of this century, not as a single explosive event, but as a steady, accelerating climb. The coming decades will likely focus on establishing the foundational infrastructure in near-Earth space and on the Moon. Orbital hubs like the Gateway and the first experimental solar power demonstrators, alongside initial lunar bases and industrial prototypes, could become operational realities by the middle of the century. This phase is about proving the core technologies of living off the land and building in space. Following that, from around the 2070s onward, the focus would shift outward. We could see the first permanently crewed stations on the Martian moons, the opening of profitable asteroid mining outposts, and the beginning of construction on the first large-scale rotating habitats at Lagrange points. These projects represent the maturing of our off-world economy. Finally, by the century's end, the most ambitious and patient endeavors would reach fruition: the completion of the first full-scale O'Neill cylinder cities, the launch of the first interstellar probes like Starshot, and the establishment of permanent scientific outposts in the distant outer solar system. The feasibility of this entire grand sequence hinges not on miraculous, undiscovered physics, but on three very human factors: sustained investment, international cooperation, and relentless incremental progress. The technologies required, from advanced robotics and new materials to closed-loop life support, are already in active development in laboratories around the world. The true challenge is one of will and coordination. It requires a commitment to fund the decades-long research and development cycles, to share the risks and rewards across nations, and to patiently solve each engineering puzzle as it arises, learning from both our successes and our setbacks. This is not a random collection of science fiction dreams, but a potential cascade of human achievement. Each completed structure would generate new knowledge, new wealth, and new capabilities, directly funding and enabling the next project on the roadmap. The journey from a lunar outpost to a city among the stars is paved with these logical, cumulative steps. This interconnected blueprint reveals a future within our grasp, built step by logical step from the technologies taking shape in our labs and launch facilities today. We are not waiting for a miracle, we are assembling the toolkit. Reusable rockets are already rewriting the economics of orbit. Robots are learning to assemble structures in vacuum chambers. New materials stronger than steel are being woven at the molecular level. Each of these 20 megastructures represents the next logical application of a capability we are actively mastering, transforming the grand narratives of science fiction into the practical engineering challenges of tomorrow morning. The vision they collectively paint is of a century defined not by earthly limits, but by cosmic ambition. It charts a clear path from our current foothold in low Earth orbit to a future where humanity is genuinely interplanetary, economically vibrant across the solar system, and engaged in scientific discovery of profound depth. This is the potential legacy of our generation, to be the architects who laid the first cornerstone in a cathedral of civilization that spans worlds. The most compelling thread running through every concept is interdependence. The lunar mass driver enables the orbital power satellite, which funds the asteroid mine, which supplies the rotating colony. Each success creates the capital, both financial and technological, to attempt the next greater leap. This is how species-scale projects become reality, not through a single Herculean effort, but through a cascade of confidence where each achievement proves the next is possible. As we stand on the brink of this new era, gazing at the blueprints spread before us, the fundamental question has shifted. It is no longer a matter of pure technical capability, of asking, can we build these? The physics is understood, the principles are sound. The question that now hangs in the balance is one of human resolve. Do we, as a global civilization, possess the collective will, the patience for decades-long projects, and the wisdom to cooperate across borders to begin? The stars and all the wonders that lie between them await our decision. They have been waiting for millennia. If this vision of our potential future excites you, if you want to witness these blueprints slowly become reality, subscribe to join us as we track the progress of these incredible projects. And let us know in the comments below, which megastructure do you believe will be the first to rise from the pages of a concept into the silent, waiting darkness of space?